Hello and welcome everyone. My name is Peter Robinson and this is the Ethereum Engineering Group Meetup. Today we've got Stefanos, who is from Imperial College London, who is going to talk about ZK technology and vulnerabilities, which is an awesome topic. And so over to you, Stefanos. Do you want to introduce yourself and then maybe present your slides?
Yeah, thanks a lot, Peter, for having me. I'm Stefanos. I'm a PhD student at the Imperial College London. I'm mainly doing research around blockchain, zero-knowledge proofs, and focusing specifically on security aspects of those technologies. And I'm also working in a company called ZK Security, where I think it's pretty self-explanatory what we are doing there. So I will try to share my screen now. Oops, wrong screen, I guess. Give me a second. It's funny because we did that just a few moments ago. Let me close everything up. Okay, it was in presentation mode. Let's start. Okay, you can see the right screen, right?
Yes, we can.
The presentation. So should we start?
Yes, please. And we can see the screen,
Okay.
so it's all good.
Yeah.
Go ahead.
Okay. Yeah. If you have any questions at any point, feel free to ask them at the moment and not wait for the end of the presentation. Okay, so we discussed a bit about myself. So what this talk will be about. First of all, I will give a very brief background on what are zero-knowledge proofs and especially what are SNARKs. And then I will give some motivation of why we should care about ZKP vulnerabilities, in which levels can something go wrong when we use zero-knowledge proofs, what could be the impact of vulnerabilities in the implementations of zero-knowledge proofs. I will discuss a threat model, and then I will explain how we did some analysis of various vulnerabilities and present a taxonomy we came up with. And finally, I will briefly discuss defenses and what we can do in general to prevent such vulnerabilities from being exploited. So I will start with the background, and basically here I have a definition of a zero-knowledge proof. So a zero-knowledge proof is basically a cryptographic protocol that enables one party, which we call the prover, to convince another party, which we call the verifier, that a particular claim, a particular statement is true, and potentially without disclosing any details about the claim itself. And zero-knowledge proofs have been used mainly in the blockchain space, and I would say one of the most well-known applications is ZK-S, which has done tons of progress in that space of making zero-knowledge proofs practical. But lately we have more and more usages. One very prominent is using zero-knowledge proofs for basically creating validated proofs for ZK rollups, which are some layer 2 solutions for scaling legacy blockchains like Ethereum. But also we have seen usages of zero-knowledge proofs beyond the blockchain space. For example, we can have private transactions independently of if those transactions are on-chain or off-chain. We can use zero-knowledge proofs in government wallets for proving parts of our identity and many other very interesting use cases. So the most prominent protocol are SNARKs. And what is a SNARK is a succinct, non-interactive argument of knowledge. That might sound a bit a lot of information to digest, but basically, what is the main property of SNARK is the succinctness. That basically we have a proof that is very succinct. And what does that mean? Two things, right? Let me provide an example first of all. So an example of a SNARK is that we can create a proof that can describe something like that I know a message M such that the hash of M equals to Y. And I can provide a proof about that. Now, the message could be either public or private. So I might reveal you the message or might not. But what a SNARK is about, it's the succinctness. And that means that the proof has to be both very short. So for example, if our message is 1 gigabyte, the proof should be some at most kilobytes, maybe even bytes. And it has to be very fast to verify. So even if the time we need to compute the SATA56, it's let's say 2 seconds. The time to prove the SATA56 is let's say 20 to create a proof about that we know the M that results to that hash is 20 seconds or 1 minute. The time to verify it will be milliseconds. So even if we don't care about the zero knowledge property of ZK-SNARKs or SNARKs, we still have a very nice property that it's the succinctness, and that's very important. And we also discussed about that the ZK-SNARK can basically reveal nothing about the M itself. Okay, and here is a very high-level overview of how it works. Can you see my pointer?
Yes.
Okay. So basically, we have a circuit, and I will provide an example of what the circuit is in a little bit, I think in the next slide. And we have some public statement. You can imagine some part of public information about our computation. For example, some public inputs in a function, like the hash function, and some secret statement. And that could be, for example, either some inputs or some outputs of our computations, etc. And the goal is that the prover can convince the verifier that it knows a secret statement. And that secret statement basically satisfies our circuit, given we have some public statement. And the way we're doing that in a SNARK is that we have a pre-processing phase, where basically we provide some public parameters, or we call it common reference string, to a function, to setup function, and the circuit that is known from both the prover and the verifier, and we create some public parameters, a key for the prover and a key for the verifier. And then the way it works, the prover takes the proven key, the public input, and the private, the secret statement. It creates a proof, and it provides that proof to the verifier that also knows the verification key and the public statement, and it can verify and either accept or reject the proof. Here I summarize again those three functions, but let's jump to an example. So when we use zero knowledge proofs, what it's really nice about them is that basically we can create proofs about arbitrary computational problems. And to do that, typically we have to use a domain-specific language. There are multiple different domain-specific languages. Some are standalone languages, and some are kind of embedded in other languages as libraries. One of the most well-known and used DSL is Circle, that I will provide an example here, but other examples that you might have heard of are Gnark, Hello2, LibSnark, Noir, Leo, and many other examples. So here we have a Circle example, and basically you can imagine a template as a function that takes some static variables as parameters. We will explain why that is static and why it's important. And then we defined some arguments for the function again. We have some signals, which is, you can imagine them as variables, and we can define if it is an input. So A and B are function parameters, basically. And then C is function output. And then we have our code. So what is important, and I have three different colors here. You can neglect for a bit the purple one. So what is important here is that in our circuit, we do two things. First, we perform some computation. And here, for example, we assign to the signal C the multiplication of A and B. And also we have to define constraints. So here we constrain that C should be equals to the multiplication of A and B. And the way you have to imagine that is that the computation part is performed from the prover, and the constraints are checked by the verifier. So we have both computation and constraints in the same code, and the developer has to do both. Some other details is that our arithmetics, basically, we have one type here, and that type is field elements, and it works in a modular arithmetic where we have a very large prime. And what does it mean? For example, imagine we have prime 9, but we work in a much larger primes. Everything is modulo 9, all operations. So we might have overflows and underflows. Loops can only happen by using template variables, the static variables that we mentioned. And what does that mean? It means that during compile time, we actually know, we can actually unroll the whole program. So N has to be set in compile time, which is also the time that the setup phase is happening that we discussed previously. And at that time, we know exactly how many times we will go into the loop. So we know the exact size and shape of our circuit at compile time. And all constraints must be in the quadratic form, and that's more relevant about Circom. In other DSLs, we have other rules, and that depends on the proof system you are using. Are there any questions so far? I guess I can proceed, and maybe we can go over questions later. Why we should care about vulnerabilities in the ZK domain? So at the moment, here I have some of the applications we have that heavily utilize zero knowledge proofs. We have ZK rollups, which are scalability solutions that at the moment they have around 5 billion in total value load, and that's expected to increase. Some of the optimistic rollups might become ZK rollups in the future, but that is something that we expect to increase. We have ZKs, we have other ZK applications like ZK login, which is the mechanism that people can use in the Sui blockchain to interact with the blockchain instead of having to remember seed phrases, but they can use ZK login to interact with the blockchain through their credential from Google or Facebook, etc. We have private programmable L1s and L2s, where they basically have zero knowledge proofs as first-class citizens in the blockchain. So you can develop private applications, and we have various off-chain applications that we are using in the real world. But although we have all those usages of ZKAPs, especially in the last 4 to 5 years, we haven't seen any exploits. And although we haven't seen any exploits, there have been major vulnerabilities in some of those systems while they were online. For example, ZK had a very important vulnerability that was disclosed in October 2018. It was fixed in February, around February 2019, it became public. And an attacker could actually exploit and get a large amount of ZKs out of it if it could have found the attack and exploit. Tornado Cache was also had also a major vulnerability and was exploited by the team itself to migrate to another contract. ZK-Sync, which is a ZK rollup, had a vulnerability that a white hat hacker identified and got a very large bug bounty about it, but also that vulnerability was in the live system. And also in every audit of any major protocol, and some of those protocols are already in line when the audits are out, or just before they got out, they publish an audit. Almost in all of the audits, we see major and critical vulnerabilities. And actually, the ratio is even higher than smart contract audits of critical or high vulnerabilities. But still, we haven't seen any major exploits happen in practice. And people suggest that this is because ZKPs are very complex, not many people understand them, etc. And although that might have been true a few years back, I don't think this is the case anymore. There are many resources for people to learn about ZKPs, and quite frankly, some of the vulnerabilities that could have exploited are pretty simple. So, for example, here is a circum template. And basically in circum, you can either assign a value, either with equals or with the symbol we saw previously, which is dash dash and an arrow, or you can assign and constrain a signal with that symbol. And basically, that very simple detail could have resulted in one of the major protocols that is using ZKPs to completely be drained. And that was actually a vulnerability that was public for quite a while before Kobe found it and submitted a fix, and they fixed it, and everything was fine afterwards. But it's not that complicated for someone that has some experience with ZKPs. And what has happened so far into better understanding ZKP vulnerabilities, there is a very nice GitHub repository from folks at ZeroXSpark. It's called ZK Bug Tracker, and it has some vulnerabilities and explain what those vulnerabilities are and some bug reports, etc. So what we wanted to do in our work and what I'm going to present now is trying to better understand implementation vulnerabilities in ZKPs. So here we don't focus if there is a cryptographic error in the original paper that described the ZKP protocol, but basically we go and see into the implementations and see what has already gone wrong, and what we can do to minimize the chances that we have an eventual exploit. So firstly, I'm going to present and try to give an overview of all the different layers that are involved into applications that use zero-knowledge proofs and how they use them. And I think this is very important because by doing that, we can understand what can go wrong in which part. So first of all, I split here between real world and the SNARK world or the ZKP world. So in the real world, we have some relation, some program maybe, some specification that we want to create a proof about it. And we have some public inputs, and we might have some private inputs. The first step is manually to translate that relation, that specification we have, into a circuit that we can then use to produce a ZKP, right? And this is a very manual effort, and also many things can go wrong there, and the majority of bugs happen during the translation from like the specification we have or the idea we have, and how we want to translate it to a circuit, to write it into a circuit. The next part is some front-end, right? So basically, when we use a ZKP, we have a complete compilation pipeline, and the front-end basically it's composed of two main things: the compiler and the witness generator. So the compiler takes the circuit as input, and it translates it to an intermediate representation that can then be processed by the prover and the verifier, basically by our backend. That intermediate representation, it could be a Plonky-like table, it could be some rank 1 constraint system, and there are many different intermediate representations based on what proof system you are using. The witness generation, you can imagine it as your runtime that runs during before you want to do the proving. And basically what it does, it takes the circuit, it takes the public input and the private input, and it generates your output. And it generates it in a similar format and what we are going to use in the intermediate representation. So you can imagine intermediate representation again being kind of the constraints in a specific format, and witness generation, it's like the runtime, the execution that happens to fill all the values for the constraints. And here we can have some bugs too. We will going to describe later what can go wrong there. Next, we have the backend. The backend is composed of the three main functions of SNARKs or of ZKPs, right? We have a deterministic setup phase that takes the intermediate representation and produces a proving key and a verification key. We have a SNARK prover that takes the private and the public input, which has been going through the witness generation, and it also takes the proven key and produces proof. And we have the SNARK verifier that takes the public input that has gone over the witness generation. It takes the proof and the verification key, and it either accepts or rejects the proof. And basically here in the backend, it's the closest to what we have in the papers that describe the proof systems that we are using in zero-knowledge proofs. And implementation bugs here could be because the paper, it wasn't clear how to implement something, or maybe some parts were pretty heavy and we wanted to optimize them in the backend. But also, you can imagine that in a broader notion as part of a compilation tooling framework that developers are using. And many bugs can happen here too. And finally, we have what we call the integration layer, which is basically our application. In blockchains, you can imagine that as a smart contract that consumes zero-knowledge proofs. And then it does something. For example, it can have in itself a verifier that you have got from the backend. And then in the smart contract, you call that verifier, you verify a proof, you accept it, a proof that some user has updated, and then you perform some actions based on the result of the verifier. And the way you integrate this zero-knowledge proofs into your application might also introduce some vulnerabilities because of assumptions that you might have in other layers and you don't enforce them in the integration layer. And what change we had lately is that instead of having developers to writing circuits themselves, we have built what we call ZK-VMs, which are basically some large circuit that emulate and prove the execution of a VM, for example, a RISC-V VM, and then users, instead of having to write circuits themselves, they actually provide a program to the ZK-VM, a Rust program, for example, and the ZK-VM will compute a proof of the correct execution of that program. Here it's a bit more tricky how to get the privacy part, the zero knowledge part, but it's something to keep in mind. So in that case, the circuit vulnerabilities can only happen by the people that develop the ZK VMs, but still can happen, but will be much less relevant because developers that uses as users the ZK VMs will not have to worry about that vulnerability. So you will have an extra infrastructure layer, I would say. Another way to see the workflow and the hierarchy is in this way, where we have in the bottom layer our hardware, our operator system, runtime, etc. Then we have our proof system, which is the implementation, for example, from Growth 16, which is one of the most popular SNARKs. Then we have some low-level arithmetic libraries. Here it's not the implementation, it's the paper itself, right? The specification of the protocol. And some low-level arithmetic libraries that we might use to implement that protocol. And here we have the implementation of that protocol in a front-end and in a back-end. And here I have in the parentheses what that could be for the circum case. Then we have the circuit implementation, which is a zero knowledge proof circuit that developers have to write. And finally, the application that interacts with our zero knowledge proofs, which could be, for example, the Solidity. So in circum case, we have Solidity, circum SNARK.js, which is our front-end and back-end, FF JavaScript, the low-level implementation arithmetics library that we are used in circum and SNARK.js mainly. We have our protocol and we have our operating system. And in this work, we will only focus on those four. The others could have typical vulnerabilities that happens in every software stack. There is a question?
Yeah, I just had a question about so if imagine a zero knowledge system is implemented correctly at every layer except the hardware layer, wouldn't it still be protected from the vulnerabilities of the hardware as long as the integrity of the execution is still correct?
No, right? Because when you build a system that uses whatever, if there is a vulnerability that is exploitable in the hardware and can affect, for example, your verifier or your prover, then your system will still be
Oh, I see what you're
exploitable, right? Even if, and that's something very important, right? Because if you have a vulnerability in one of the lower layers, for example, if you have an issue vulnerability in the Growth 16 paper itself, and then every implementation has been built on top of that, and even if everything above the Growth 16 layer, right, the paper, is even formally verified against the original specification, then still everything is exploitable, right?
Mhm.
Another more common example is if you have a backend vulnerability or a front-end vulnerability in your infrastructure, and maybe you have put a lot of effort, a lot of money to formally verify your circuits, to formally verify your Solidity code, but if you have a vulnerability in the backend, and to formally verify the backend and the front-end, it's a different beast, much more difficult. Then it still could be exploitable, although you have all those formal proofs and all those formal methods that you have used. Does that make sense?
Yeah, that makes sense. I guess within the blockchain application, with some of these things being distributed across a network, um, if there was a vulnerability, uh, how do the how do the verifications come into play in order to
So
either identify a vulnerability or a bad actor within the network, um, since the risk is being distributed across the whole network in that case?
I guess your question is specific to Ethereum or not? It's because, for example, in Ethereum, we have multiple different clients that implement the EVM, or is it multiple different parties that run the same software?
Yeah, I guess my question is just generally, but just any blockchain really. Ethereum
Any
would be a
blockchain,
good.
if you have like the same client run by every different network participant, then if you have a bug in that client, that's exploitable, right?
Got it. Okay.
If you have different clients, then yeah, it's more difficult to exploit it because there will be differences in the consensus layer of the blockchain, and then, but that's independent of the ZKPs, right? That can happen
Yeah.
in any blockchain program you might run.
Okay. Thank you.
Okay. So let's proceed. So what are the main properties zero knowledge proofs provide? It's knowledge soundness, which means a dishonest prover cannot convince a verifier of an invalid statement, except with a negligible probability. We have perfect completeness, which means that basically an honest prover, a prover basically, can always convince an honest verifier of the correctness of a valid statement. So if something is correct, you can always produce a proof about that. And zero knowledge means that the proof pi we have does not reveal anything about the private part of our computation beyond its existence, beyond that we know that it exists. And those are the three main properties that zero knowledge proofs provide to the user. What is our threat model? We have basically three adversaries. We have the network adversary, who basically can observe the system and all the public values. He might have access also to the circuit, but it cannot interact with the network, with the system. So what that attacker can do, it's just if the ZKP, if the zero knowledge property is broken, it can gain some information. We have the adversarial user, which basically can submit inputs to an honest prover for proof generation, and he has control on the inputs that goes to the prover, right? So that is capability. And then we have the adversarial prover, right? Who basically can try to do whatever he wants to try to trick the verifier. So this is the strongest adversarial we have. And quite frankly, most ZKPs protocols, most applications that use ZKPs, eventually want to have the assumption of working in an adversarial approval model because only then they can provide true value to their users in most cases. I have an example here to try to explain the difference between adversarial user and adversarial approver. I will try to do it quite fast, so maybe it's not that easy to comprehend. So imagine we have a ZK rollup. What is a ZK rollup? It's basically you have some node that runs some blockchain that basically it's going to produce some proofs and submit some proofs and transactions to an L1 contract in another blockchain. So our L2 sequencer and prover can be honest and we can trust it in a setup where it's very centralized. Our ZK rollup is very centralized. We have just a sequencer, just a prover, just a blockchain node that runs the whole L2 ZK rollup, and we trust it. And in that case, we have an adversarial user setup, right? Because our adversary can only be the user that submits some transactions that might try to do some weird things, but it doesn't have any control on how the proof is produced. A better model is we can say we have a decentralized network and we don't trust the L2 operator, the sequencer and the prover. And in that case, we have the adversarial prover, right? And that means that our zero knowledge proof, our circuit should be correct, so the verifier cannot be fooled. And that's the model we mainly want to work on. And what can happen? What can be the impact of ZKP vulnerabilities, you can break the soundness, so a prover can convince a verifier of a false statement. And for example, in ZK rollup, that could mean that you can generate proof of invalid transactions that send all the funds in the blockchain to a specific address. And we can break the completeness, which means that basically we cannot verify proofs for valid statements, or we even, because of a bug in our circuits, we cannot produce proofs for some valid statements. And we can have breaking of zero knowledge, which means there is an information linkage about some of the private part of our statement. So what we did is we analyzed 141 bugs, and by bugs I mean security vulnerabilities, and our sources were audit reports, vulnerability disclosures, and from various bug trackers of some of the most prominent protocols. And we only cared about kind of high or critical vulnerabilities. So for example, in audit reports, we didn't consider informational or low or medium bugs or findings, but only highs and criticals. And we also did not consider non-ZKP related vulnerabilities. So we didn't include any reentrancy vulnerabilities, etc. And here are our results. So here is the impact, soundness, completeness, and zero knowledge. And here we have the layers and the total. And we can see that basically the most vulnerabilities happen in the circuit layer. And also most of those vulnerabilities are soundness bugs. And soundness bugs are the most important ones, right? Because you break the main property. The property that the proof basically, if you verify the proof, you should accept the result as true. And that could break many of the protocols that have such vulnerabilities and break them completely, right? And completely, we mean by extracting value out of it, and not just a denial of service kind of attack, which is the most common case for completeness bugs. So why do we have so many vulnerabilities in the circuit layer? The main reason we identified is because of the extra complexity that we have when, as developers, we try to write ZK circuits. And what is the extra complexity? Is that as developers, we should take care of both the computation part, which is what the prover does, and the constraints part, which is what the verifier checks. And here I have a one-to-one mapping of like some computation and some constraints. But in many cases, what we are actually doing when we write ZK circuits is that we try to optimize our circuit, or in some cases, we can't even one-to-one map the two because of the nature of the constraints that we should define. But let's say in the optimization example, basically what we are trying to do is we are trying to add as less constraints as possible. So instead of constraining every intermediate step, we are going to create one more complicated a bit constraint that will capture a lot of computation. And by doing that, we might have under-constrained issues. Basically, we have less constraints than those we require. And as such, a malicious actor can exploit that and try to convince us for something that we didn't really want to accept, but based on our constraints, we'll accept it. Another reason is because many times in zero-knowledge proof circuits, we try to implement quite complicated cryptographic protocols. So, for example, we are trying to write circuits that prove ECDSA signatures inside a circuit. and that would also introduce many issues. Here I have some examples just to give you a notion of not vulnerabilities, but how things are implemented. For example, in Circle, we have both the constraints and the computation in the same code, and you have to try to, for example, here is the example where in the end we add the constraint, and here we have some computations, some extra constraints. Or in, for example, Hello 2, we have a different setup where we define some constraints in one function and we defined the computation in another function. So there are multiple different ways of doing that. Some of the most modern ZKP DSLs actually have the default mode of everything that is a computation. It's also constrained, and you can use an unsafe keyword to separate them and do something that's not constrained and then add manual constraint, which is a better model because you can reduce many of the vulnerabilities that can happen. So what are the main vulnerabilities that can happen in the circuit layer? Are under-constrained issues, which is what we discussed, over-constrained vulnerabilities, which is basically in having more constraints than those that you need, and that could result in rejecting some results, some values that you wanted to accept. And then we might have computational hint error, which is a different kind of vulnerability. It's more about how you do the computation and issues you might have when you do the computation. And it doesn't have to do with anything with constraints. And in our paper that we'll provide the link later on, excuse me, we provide a complete root cause analysis about different vulnerabilities we identified. Here I will split them in 3 main categories, but you can look at the paper to see more examples and see exactly what's going wrong and why those bugs happen. But I would say the 3 main categories are reasons why we have these vulnerabilities are because we have a very different programming model than traditional programming, that it's more complex. We have mainly the need of doing aggressive optimizations and also expose cryptography at the outer level, at the developer, to actually have to implement low-level cryptographic primitives in circuits. And finally, we have common errors that we also have in any programming language, in any programming model, like API misuse. I have some examples here, but I will skip them. I suggest looking in the paper to try to understand them. So I will proceed now to the next layer. And in that layer, basically, it's the integration layer. It's the layer where we use the circuits. And we have 4 main vulnerabilities here: passing unchecked data, proof delegation error, proof composition error, and ZKP complementary logic. To give you a feeling, I will just explain what is passing unchecked data. So imagine you have a smart contract, and that smart contract calls a SNARK verifier, where here is where we call it verifier dot verified proof. In our circuit, we might have some assumptions, and we might have those assumptions to reduce the number of constraints. For example, we might not check if any value that passed to the circuit is less than our prime field we are using in the circuit. And we do that to reduce the number of constraints we will have to check in our circuit. And we do that because basically the number of constraints relates to how expensive it is to do the proving and the verification. So we are doing that. And now that we have that assumption in our circuit, we have to enforce that assumption in the outer layer, which is the integration layer. And if we forget to actually check that whatever we are going to pass as an input to the verifier is less than the snark field, then someone can exploit it. And basically, it will exploit an overflow vulnerability by providing something larger, and then it can trick our system and exploit. And so what is really important is to have a complete understanding of all the assumptions we have in different layers and to enforce them in the right level. Next, we have front-end and back-end vulnerabilities. In the front-end, it's kind of typical compiler vulnerabilities. For example, you might have some optimization phases in your compilation process in the front end, and in those optimizations, you might have a vulnerability that could lead to basically remove some of the constraints that shouldn't optimize that, for example. And that could be an error that could lead to many issues when people use your compiler. And then in the backend, it's basically issues where we don't implement the ZKP functions, set approver and verifier, and the verification as intended, as we had to implement them in the backend. And that could break the whole protocol and all the applications that use that backend. How much time? Okay. I will conclude with that. So we have those vulnerabilities, but there is already some effort to use security tools to detect some of those vulnerabilities and try to prevent them. So here we have circuit layer, front-end and backend. And we can see that the majority of tools are in the circuit layer, and especially for other constraint vulnerabilities, which is good because it's the main issue at the moment for zero-knowledge proofs and the constraint issues. But we are not in an ideal situation because most of those tools are for a specific DSL. For example, most of them are for circuit, and most of them also can only detect part of the under constraint vulnerabilities. And some of them, for example, some formal verification tools like Picus, which is one of the best tools we have, do not scale pretty well. So if you have large circuits, then Picus most probably won't be able to analyze their circuits. The same for Cyber also. To give you a very brief overview of what we have some static analysis tools. We have some tools that kind of doing symbolic execution like Pacus and Correct by utilizing SMT solvers to try to identify vulnerabilities. We have some web fuzzer that, quite frankly, it's kind of difficult with fuzzing to find those vulnerabilities, and especially with kind of traditional fuzzing. But what we can also see is that in the front end and in the back end layers, we don't have much support from tooling. So I think that's a clear field that we should put some effort to develop some methodologies to be able to automatically detect issues in those layers. And basically that's it. I will conclude with why do we have bugs? I would say mainly because ZKPs are not just math, there is also implementation. And then there is a nice quote from Ron Rivest for one of the specifications from the 90s for digital signatures. And the quote was, "The poor user is given enough rope with which to hang himself." And I would say that quote really matches the current situation and ZKPs, because we expose all the optimizations and all the cryptography to the out layers, and developers really can mess things up. We also, in some DSLs, miss of fundamental abstractions, and quite frankly, newer DSLs provide nicer abstractions that could reduce many of the vulnerabilities we saw in this work. And we have a bit of complexity in different threat models than in traditional programming that developers should be aware of. And one other reason I would say it's lack of specification. We don't have enough specification in all of the layers, in the proof system, in the backend, in the front end, in the applications, in the circuits. We don't write enough specifications and documentations to make sure that things are working as they should work and to have a clear understanding of what's going on. And what can we do? Basically, we need more learning resources. Basically, it's negate all the previous one. We need specifications, we need easier and more secure programming languages, and we need better testing and security tools. So here is also a link, a QR code that if you scan it, you will go to our paper, but also a link for a data set where we try to reproduce all the vulnerabilities we had in that paper. And we are in the progress of doing that. That's basically it. Thanks a lot for your attention. And I'm happy to take any questions you might have. I think we have a few more minutes.
Yes, thank you for an absolutely awesome talk. So I know I've got a question, but before I lead off, does anyone else have a question?
I just had one question. I noticed that in this particular conversation, we were talking about snarks in general. Are there any trade-offs when it comes to using snarks in terms of more security but less performance? Or what are the differences between those types of approaches?
I would say that basically the programming model is pretty much the same, kind of. So in the circuit layer, you can have similar vulnerabilities. What does it change is something we didn't really discussed here, but basically in the deterministic setup, in SNARKs, you need some common reference string that is produced by a multi-party computation that you have to have at least one honest participant in that process, whereas in STARKs, you don't have that. And that's a huge deal on your assumptions in a more formal cryptographic way, and that's the main difference. But what we discussed about the circuit layer, the front end, the back end, the integration, and all the vulnerabilities that can happen there, it's pretty much the same.
Okay, thank you.
Yeah. Good. All right. So my question was, so there's we're having RISC-V ZK VMs coming over the horizon, and where you can say use ref in combination with them to get, say, a full ZK EVM. And to my mind, that feels like a better approach, where you're just not getting, the average software developer isn't going anywhere near the actual circuits. And I guess you'll have multiple use cases using that one, say, RISC-V ZK VM. Do you agree, or do you see that as a real improvement, or are there things to watch out for that might not be obvious?
So what we do have in that case is that basically instead of having the circuit implementation, we have the ZK VM circuit implementation. In the case of the example of ref, where basically instead of writing the circuits, you write the circuits for a RISC-V VM, which might be simpler than writing circuits for an EVM, and then providing the rest to it as an input. Basically, there is a trade-off, right? It's much slower than what we currently have with custom circuits. There are ways to improving it. For example, one solution is to write precompiles in the VM and have circuits for those precompiles to speed up the critical operations that people have been playing around with. I would say it might be safer. It might be better because it might be a bit simpler to do formal verification, but there is a trade-off of speed versus having something more maintainable, I would say. And maintainable because if there is a change in the EVM at some point that you need to implement, you don't have to change your circuits, but you have to just update the red that you provide to your ZK VM. And that's a huge plus. I would say that still there could be bugs in the ZK VM circuits, as there could be bugs in the ZK EVM circuits. And pretty much similar people wrote those circuits. It's not that the end user in that case of a ZK rollup writes those circuits. But we have still the need for ZK DSLs and ZK circuits in cases when we need to have client-side proving. And that means any application of zero-knowledge proof that actually requires the zero-knowledge property, you can't run in your mobile device a RISC-V ZK VM to produce a probe. It's virtually impossible. Maybe it's possible in some cases, but it's very difficult and very expensive to do it. So for using the ZK property, we will still need to have circuits, at least in the near future. Maybe in the future we'll change that down the line, but yeah.
Okay, all right, well, great, thank you. Can you flip to those last slides right at the end there? And
The conclusion?
yeah, no, after that, let's just go to the go to the t-shirt slides because I think we're right
Yeah.
at the right on time. But so everyone, there's the merch store is still open and some of the t-shirts. Next slide is there's a whole stack of forthcoming talks coming up over the horizon. And then one more slide is, and there's a whole, if you're here today, this recording of this will be on YouTube. If you want to ask the speakers tricky questions, join the meetup group and RSVP and get the link. And there's a Slack workspace if you want to chat with people, and sometimes there are examples, and in which case they're on that repo. So before we finish off, are there any final questions for Stefanos? All right. So look, thank you very much. I've learned a lot, and I've been working in this ZKP space for years, and I learned stuff. So, and yeah, this is great. I read the paper, and even after reading the paper, I got stuff out of this talk. So yeah, thank you. You've done very well.
Thanks a lot. Thank you for having me.
Yeah. All right. See everyone in another 2 weeks' time, and have a great rest of your day. Bye-bye.
Bye.